bit. So welcome back to our JavaPlex lecture. The data is actually from this website. I did some very, very minor processing, and I'll show you exactly what I did from the data that I downloaded off of this website by clicking right there. And then made very minor modifications to create this thing. And you can get that from my website if you want to follow along today, or you can just listen and follow along later. So this data actually has 3 columns that corresponds to 1 patient. We're going to have each patient being our data point. So our patient will correspond to a data point, but we've got 3 columns, and we're actually not going to take all 3 columns. So for each patient, so the matrix you will see is just basically a whole bunch of columns, and every 3 columns go to a different patient. The first column is the log 10 intensity, the second is the log 10 ratio, and the third column is the p-value. Let's first talk about the log 10 ratio. If you remember, people, to do this microarray data, you have the patient DNA, a control DNA, or RNA, depending upon what it is you're measuring. You mix these 2 together, they compete, and then they bind in this well to some complementary DNA, and whichever you have more of, you hope that, so if your patient DNA is marked with a red fluorescence and your control DNA is marked with green, if you have more red DNA than green DNA, you expect it to be red. If you've got more green than red, you expect it to be green, and it's very likely to be a mixture of the 2. But of course, nothing in biology is perfect. Suppose you have a 50-50 mixture of red and green. Well, that means that you'll have a nice distribution where maybe it's an equal mixture. Maybe in some cases you get 40% green binding. In other cases, maybe you get 40% red binding. And so when it's an equal mixture, sometimes it might appear more red, sometimes it might appear more green, even though it's an exact mixture. Versus if you've got 90% green, well, then you're still going to have a nice distribution. But if 90% is green, then when you go over here, you're still going to be mostly green, mostly green. It's going to be a while before you get the red stuff. So in other words, when you have the log 10 ratio, you believe the data more when it is either very red or very green. And so since this is a log 10 ratio, if it is a large negative number or a large positive number, I don't really have any large positive numbers here, but if it's either large positive or large negative, you're more likely to believe the data, versus if it's a number close to 0, where the ratio is pretty equal, then we don't really believe the data so much. So log of 1 being 0, we don't believe it fits around here. But if it is, 1 to 9 or 9 to 1, then that ratio, whether positive or negative, becomes more believable the further away it is from 0. The log 10 intensity, however, is you might have a well where very little binds. So you might have almost nothing binding, and so you might have very low intensity. If you have low intensity, then the data is not very believable. So in this case, the larger the number, the more believable it is. If you don't have very much binding going on, then maybe something happened to the well. Maybe you just don't have a lot of DNA. If you don't have a lot of DNA, small sample size, it's just not as believable. So you care about, you would like the intensity to be high and the ratio to be either high positive or high negative. After you do the log 10s, either 1 to 9 or 9 to 1 would be good. 50-50 is not so great. And you put these 2 together and you take the p-value. So if we were to really process this data, we would take things with the appropriate p-values, put a cutoff, and then choose only those, and that's what we would look at. However, we're not going to do that today. Today we'll just take all the data, but the data that we're taking is just this middle column. So we're only going to take a look at this middle column, and we're going to take a look at all the data, whether it makes statistical sense or not. And then later on, probably in November, we will discuss data processing. We might very well do it earlier. If you have your own data to analyze and you've got questions about it, let me know. I did send an email that hopefully everybody got. If you didn't get it, send me an email. Let me know if you do want to analyze data. Whether or not you have data to share, let me know what type of data, because then I can sort of, bias my lectures towards those sorts of things. But in terms of following the IMA schedule, computational biology is being covered in December, and so November is sort of the time we should be talking about processing data. But we can be specific in, before that. So if there's anything we want to discuss before that, let me know. But otherwise, we'll do the formal processing in November, beginning of November. So we'll take our data. We will take only every third column. So we will only take these columns right here, just every third column. And we will delete these two, and we will ignore the intensity. We'll ignore the p-values, although in reality, we should be considering that when we choose what data, how to analyze this data. So these are the commands that we will be entering in to create our data matrix. So I will go ahead and copy and paste from this sort of thing, but just to keep in mind, we will always have to load the JavaPlex library. If we don't load it, nothing will work, and it should actually be loaded first. I tried to do all the MATLAB stuff, so this is a MATLAB command, so I tried to do that first, and then I loaded JavaPlex and erased everything. So you definitely want to do this command first to load your JavaPlex library, and then we can go ahead and load in. At the moment, my data has some text in the first two rows and the first column, so I remove those and I start off with, moving further along. And then just because I want to see the output, I'm not going to actually be taking very much. I'm only going to be taking, this is going from, counting from 0. So we'll go from, counting from 0, rows 2 and 3, and then columns 1 through 21, and we will actually see the output because I didn't suppress the data with a semicolon. So I'd kind of like to see what's happening, so I'm not taking very much data to begin with. Then after that, we will go ahead and do this for loop. We're basically going to take every third column, just that middle column for all the data points, and that we will take to be our D. So our data points are now the columns. So before they were every third column. So before we just wanted every third column. Now we've taken every third column. Our data is still our columns. But JavaPlex assumes our data is in rows. So I went ahead and did the transpose of it. Although much of the output, it will then output it as columns. So we'll just try to keep those things in mind, and then I'll just get the size of my matrix so I see how many data points we have and what dimension we're in. So size, we will get, rows by column, and so we can see our rows will be the number of data points because we did the transpose, and now our rows are our data points, and the number of columns, that will be the dimension that we're working in. And so depending upon how many points, actually dimension -1, because if we have just a single point, that gives us a vertex. 2 points gives us a line segment, etc. So I shouldn't say 2 points. In terms of our data, no, it is actually, sorry, it is dimension. So if I just have one gene, we have a one-dimensional point. If it's two genes, then we'll have a two dimension. So it is actually dimension, not dimension minus one. So we will then decide to use the standard Euclidean metric. So this is what we will do to get our standard Euclidean metric. I will put in these commands very soon, but instead of going back and forth between full screen, let me also mention that we don't have to use the standard Euclidean metric. So if you remember, this I'm taking from the macro data because no one has, as far as I can tell, analyzed this data using homology, and I think you will see why when we analyze it using homology. But with the macro, remember, they used a variety of different distances. And the main thing is we wanted the distance from the norm. And so the filters were actually a filter getting us the distance from norm. In the 2013 paper, we used Pearson correlation for distance. In the 2011 paper, they used this sort of projecting onto, so your healthy state model was sort of, you created a collection of vectors that sort of said if you were healthy, your vector would lie in this space. If you had cancer, your vector would not lie in this space. And then we measure the distance between our healthy state model by projecting your vector onto, your cancer vector onto your healthy state model. And this is the vector. And so if it had coordinates x sub I, we could do the LP norm instead of the standard Euclidean distance. Oh, and then take it to the kth power. And so in the 2011 paper, they did this LP norm for p equals to 1 through 5, and then took that to the kth power from 1 through 10. The higher these things, the more the difference from norm would become apparent. And so the figure in the paper was p equals to 2 and k equals to 4. In other words, there's a whole bunch of different distances that one can use, lots and lots of distances. And so one might want to not use Euclidean distance, so instead we can choose our own distance matrix. Because I didn't want to have to type one up, there's lots of different distance matrices one could do. I did a really stupid one. This is the 7 by 7 matrix with all ones. And this is the identity matrix 7 by 7 again. And so I just decided that the distance between all my data points was 1. Unless it was actually the data point itself, so the distance between, vertex 1 and vertex 1 was 0, of course. And then we can use this command to create our distances. And so we will now go ahead and see this. So let me escape this thing right here. And now let's go ahead and take a look at our, first off, let's look at our data. So this is the data that if you download it from the MKI database, this is what it looks like. I'm going to first search for this thing, NAN, and you'll notice I find it right in the middle of my data. And worse than that, this NAN can actually appear within the column that I actually want to analyze. So in terms of my ratios, you will sometimes see NAN. Sometimes data is missing. This data, we don't have it. And so when I calculate the Euclidean distance isn't very good at using NAN and using the distance. And so I just went ahead and I replaced all my NANs with 0. If I would do real data processing, I would just have thrown it out. I would have done something else. Maybe I would have used 0 because after all, I want distance from normal. So if I just say that this thing is 0, if my control were the healthy data, so maybe we have just as much red as green, so maybe 0 would be an appropriate replacement. Maybe not. We should take a, better look at it. I just replaced all of them with 0 because it was easy and obvious, and that way we could work with the data. The other thing that I did is if I go back over here and search for comma, I'm entering in CSV, comma, delimited format, and so if I've got commas in some of these things here, so you see there's a comma here. Well, first off, this is the very last column, this very last column, I don't need that last column at all. And so I went ahead and I just went ahead and I did edit, delete. And so I deleted that entire last column. In fact, there seemed to be a few more, so I just went ahead and just randomly went ahead and deleted all those columns past the data. So my data ended at ED, and so I deleted all the columns past things. If I then search for comma again, oh, that's because I have things selected. I don't want things selected. So let's see. I don't want to select things at all. But if I go back over here, it's thinking about things. So when you're working with this large data set, you can have some problems with things taking time. But notice, by the way, if you do want me to blow things up any bigger, let me know. But there actually is a comma in this thing. If I go over and look at it a bit more, there's a comma, pancreatic ribonuclease, comma, HP-RNase. So I could have just done a query replace and replaced all my commas with, say, periods. That would have worked. But instead, I went ahead and I deleted this column here as well. So it's going to be thinking about it for a while, but it will delete this. And so that leaves me with this one right here. So now I have where I want to eliminate the first two rows and the first column and start taking things from here. And notice that our first data point, so now it was doing that deletion and stuff, which we don't want. So let's go back to the data we actually do want. So you'll note that once I actually, so when I take a look, delete the first column and the first two rows, I will get a matrix that will look like this. After I take every third point, I'm going to want the minus 0.048. So to make sure I got the right formula, we can pay attention to those numbers. So let's actually now go ahead and start doing our MATLAB stuff. So I will go back up to here, and I'll just go ahead and copy these things here. And I will get out MATLAB. I don't have MATLAB on my screen, on my computer, and so I'm running it locally off of I'm running it not locally off of a Linux box. Instead of risking using No Machine with its thing and going back and forth between PowerPoint, I don't actually need any pictures on this one here, and so we will just go ahead and put in all those things. And now let's see if we can scroll up here a little bit. Don't need the winner to be quite so much. So, well, so we can see that because I blew things up a lot, we get quite a bit shown to us. But if let's see if I can get this without making too many people. So went ahead and let's just go ahead and put this thing back in and do our CSV read. And so now we can see that I have my 21 columns, and I just took 2 genes, so I only took the first 2 genes. Then after that, we'll go ahead and just look at an element of it. That's that element that I wanted in the second column, first row. Then we'll go ahead and run this for statement. And now if I want to take a look at my matrix D, I can do that. I've got these 7 columns, and you can see that I've chosen the right thing right here. I've gone ahead and chosen that minus 0.048 and every third column. So we now have the data that we want, except we need it to be the transpose. And so R is what we're going to do. I use R for rows. if you look at the tutorial, they use point cloud because this is point cloud data. And then we can see the size if we want to. We can see it is 7 by 2, which means I've got 7 data points, and it's 2-dimensional. Any questions about that? So we now have our data put in. Well, a small part of the data, we could put in a whole lot more if we wanted to. I've got that at the very end, but it's nice to be able to see what we're doing. So now we're going to go ahead and use our Euclidean thing. So let's go ahead and put in all of this. And we'll do one at a time. So I've just created this object called m_space. I can call it whatever I want to, but it will now have a lot of information regarding Euclidean distance between the points. I can first just get my very first point. So my very first point, remember the first coordinate, you might have forgotten the second coordinate. This is actually the row. So it's now displaying it as a column, but I needed to enter in the data as rows. But it's displaying it as columns. And now I can also get the distance. So that was, if I go back here, this m_space distance. So I created this m_space up here. We showed one row in it, displayed as a column, and now I can get the distance between 2 points. So now I'm getting the distance between 0 and 1. Oh, and by the way, you will have noticed that sometimes some of these commands are indexing starting at 0 versus other commands started indexing at 1. So that's why I sometimes will frequently print an element to see, did I index from the right spot? I think it was when we were reading in the matrix that we were actually reading from 1. But now that was not a JavaPlex command. Now that we're doing JavaPlex commands, we are reading starting from 0, numbering from 0. So we now can get the distance. So that distance, oops, I suppressed my data. I didn't want to suppress the data. Oh, that was the m space. I want the distance. Now this is hopefully the distance. Yeah, so now I'm going to calculate the distance, and I can see that that's the distance. I wanted to confirm that that was really the Euclidean distance. So what did I do? I subtracted off the 2 first coordinates of my 2 data points. So for these 2 points, my 0 and first, so I subtracted off the first coordinates. I then squared them. I then added that to subtracting off the second coordinates. You can see I did my standard, triangle inequality, and sure enough, the distance between those 2 points is 1. And the 2 points that we're talking about is I can get point 0 and I can get point 1. So if you calculate the distance between those using standard Euclidean, that's the same thing as this command right here. So we just needed to run this command to create this object that had both our data points in it as well as our distance saved. But we might not want to use standard Euclidean distance, so instead I can use these commands. So here. So first, this is similar to what we did before. So if I compare this thing to my M space here, this is this, not quite, these 2 commands are basically the same. It's just in the M space command, I'm saying let's use Euclidean metric. Versus in the dist space command, I'm saying let's go ahead and use the explicit metric. And the metric that I am giving is this dist one. And so if I go back and just say dist, well, this is what my dist looks like, where if I make it a little bit wider, I should be able to see all the 7 columns. So this is now my distance matrix, where the distance from I to j is equal to 1, as long as I does not equal to j. If I equals to j, then of course the distance is 0. So that is what I chose to be my distance. And so now when I do this command right here, putting this in as my distance matrix, so you can create any distance matrix you want. So MATLAB can calculate the LP norm for you if you want, or it might use density. There's all sorts of Pearson correlation, whatever distance you want to use, you can go ahead and put that in and put that thing in. And so now I can do similar sorts of things to what I did before, is now I can ask for the distance between 2 points. Surprise, surprise, it's 1. We set it equal to 1. I could also ask the distance between, the point in itself, and I get 0. So that's the two ways. It's this either metric, implicit, explicit, where you're choosing the distance, or if you just want to use standard Euclidean space, then you can just use this command to enter in your data. So you've got those two different ways to enter in our data, depending upon what distance we want to use. We can now calculate the Viator-Scripps complex. There are, by the way, lots of other complexes that we can create, but we will stick with the Viator-Scripps complex. One of the reasons that you might want to create other complexes is if you have too many data points, the program might take forever and you might have to wait the rest of your life to get the actual result. And so one frequently will actually sample from your data, and there are very well-known algorithms for doing that, landmark and witness complexes being very common used. So we will talk about that probably starting on Friday and then continuing on to Monday, and then we'll talk about using JavaPlex with those types of complexes as well. But for right now, we actually don't have that many data points. We only have 7 at the moment, and even when we look at the real data, we're only going to have 35 for this particular CSV file. Now, there were several Excel files that I downloaded from MKI. And so if you do combine all those, you do get maybe close to 100 patients, or close to 100 data points. But that's still not a whole lot of data points. Our dimension will be very, very high, but it still will not be a problem. We'll still be able to analyze the entire data set. So let's go ahead and take a look at what this does. There are several things that we can do. One is the maximum dimension. You may want to, so our data set is 2-dimensional, so I actually don't even need to go up to 3. So maybe I will actually just set my dimension to be 2. Our real data is more than 20,000 dimensions. So maybe you don't want to calculate H sub 2000. Maybe you want H1, H2, H3, but maybe you don't want H2000. If you do want H2000, well, see how much you want to wait. In other words, you might want to try out a few smaller values before you put in some larger values. If you seem like you're waiting too long, you can always kill it by doing Control-C or Command-C, depending upon which operating system you're using. Try a bunch of Function C's, Control-C, one of those should kill it. Usually Control or Command-C will kill it if it takes too long. But we'll start off with some lower values. The other thing is your maximum filtration value. That's actually your Tmax right here. So we will take 4 and then divide it up into 100 different divisions. And so that's the number of different divisions. So remember, we're going to be growing. Let me actually put this back into slideshow so I can write on this thing right here. So remember, we are taking our data point, and then we grow the radius. Well, these are our radius. So we've got our R0 radius, our R1 radius, our R2 radius. We generally, computer programs don't like calculating things for an infinite number of items. And so it basically partitions these things into different radii. And so we have a bunch of radii. And so then we have our maximum radius over here. That would be our Tmax. And that is this value right. This value right there. And our number of divisions, that is Rn. So this is our Tmax. And then just to say this will mean that we can calculate H0, we can calculate H1. Actually, I think I'm going to have to put this back to, there are no three-dimensional objects. Oh, I don't want to calculate H2 because since this thing is, no, I do this, let's see. I have, oh, sorry. I could actually go up all the way into H7 because I have 7 data points. I don't care about the dimension of my data. Sorry about that. I care about the dimension of my simplicial complex. That's what I'm interested in, is the dimension of my simplicial complex. And I've got 7 data points. So at some point, I might just be joining a few edges, but once a triangle forms, we're doing via torus rifts, we get the 2 simplex. And once all my data points are connected, so eventually all my data points will be connected, and I will get, since this is 7 points, I will get a 6 simplex. And so I actually can talk about going from C6 to C5. And I can also talk about C7. It's just, in that case, it's 0. And so I can actually go a little bit higher if I want to. And so maybe I will change this thing to 6 and see if I get anything more interesting. So sorry, I should have actually gone higher, not lower, to 6. So it doesn't actually matter how big, what dimension this point lives in. We're talking about the dimension of the simplicial complex. So this is the dimension of the Ripps complex. It's the dimension of this. And if my Tmax is large enough, eventually I will get this this 6-dimensional 6 simplex consisting of all 7 points. So any questions about that? So I enter in my matrix R or the distance matrix. I can do that either once. I can do either R or I can do the distance matrix. So if I want to use the standard Euclidean distance, then I might as well use R. But if I want to use a different distance, then I can put in the dist instead. So either of these two will go in for our data points. So you can put in either your actual points or your distance matrix. Then we put in our maximum dimension, which could easily equal to the number of data points we have, or more likely we don't want to go that high because it would take too long to calculate. And then our maximum radius. So if we knew how far apart our points were, then we could go ahead and set that to be our maximum radius if we so chose. And then the number of divisions, we can play around this to see where is, we're calculating this, growing it. If we do too few growings, then we will go, if I only do one, I'll go from my 30, actually I only have 7 data points. I'll go from 7, disjoint data points, disconnected data points, to the entire 6 simplex. And that would be a very boring, sequence. So we won't get a very interesting barcode that way. So we want to have enough of these things so we don't join everything right away. So this is something that one would have to play around with to see what the best values are. I do not actually have good values here. So we'll play around and see if we can get better values. But many of these points are actually very close together. Remember, they were all breast cancer data, all of whom who have actually survived. So there's actually a lot of similarity between these points. So their distances have some similarity here. Okay. So that is, and then after that, we can go ahead and calculate our persistence. And when we calculate our persistence, these are exactly the same commands that we used last time. So if today is Wednesday, then on Monday, we chose our maximum dimension, and that was, do we want to calculate H6 or not? Do we want to calculate H100? And then this was, our 2 was, do we want to use Z mod 2 coefficients, or do we want to use Z mod P coefficients where P is any prime? And it does have to be a prime. One could do the algebra if it's not prime, but then it's much more computationally complex. You have to be, it's much more, it's not as nice. It's much, much better if we have a nice prime number, because otherwise we could get into trouble. We do need the division algorithm. And without the division algorithm, as long as it's prime, then we're in good shape. We actually can do this over the integers as well, and I actually have to check. I thought this thing did over the integers, but I forgot to look up what to set P. So just try P equal to 0 and see what happens. In that case, when it comes to the division algorithm, if you have a row with 3 and 8, we don't have anything that divides 3. We don't have anything that divides 8, so we have to do a row operation. Say 8 minus a multiple, say 8 minus 6 is 2, then do another row operation to get rid of this, and then we can finally get. So as long as we can do the division algorithm, we don't actually have to have inverses, but inverses are really nice, so it's much quicker if you do Z mod P, where P is a nice prime number. So this will actually calculate our persistence. Then we saw last time we could see our intervals. We could see our intervals where we actually see a generator of them, but it may not be the best generator. So maybe you have a cycle here, and maybe that's a nice cycle, but there might be a lot of other stuff, that is actually filled in. And so maybe the cycle that you actually find is this cycle here, which is homological. It's equivalent via homology to this nice cycle, and maybe you find this ugly cycle, and that's what the output. JavaPlex does not guarantee finding you a nice cycle. There is software, and there are ways to get a nice cycle, but if I just use this command does not guarantee a nice cycle. There are ways to get nice cycles, but not with this command. And then the Betty numbers, since I am doing ZP where P is a prime, then I know that my HI is just going to be a number of copies of Z mod P to the Betty I number. And so we can get our Betty numbers depending upon, we can see the sequence, or we can just see the very last one after you've gone to your maximum radius. Okay, so I think that's enough for, these other things, we can then actually get a picture, and so this plot barcodes will allow us to actually see the barcodes via a picture. But again, there will be some different things. I can give it a file name. I can put in the maximum filtration value. So how high up in radius do I go? And then how high up in dimension do I go in terms of plotting my barcode? So we can go ahead and put in our options, and then we're going to plot intervals for our barcodes. I think that's, and then we can just run on the entire set, where I've now suppressed a lot of the output with the semicolons because we didn't really want to see most of the output, and so we will, at the very end, go ahead and run the entire data set. Any questions before I go and actually run this stuff? So let's go back through, and we've already done that. So now let's calculate our Vietoris RIPS and do this, except for we were going to change our dimension to, say, 6. And I think we can actually lower this, probably by more than that. And it's pretty quick, so we'll just go ahead and take this. Don't really know these values until after you run them. So I've gone ahead and put that in. I could have gone ahead when I took a look at this. I could have just done R6 to 100. Or I could have done dist if I wanted to put the distance matrix instead, 6 to 100. But since I want to reuse these things for the later commands, it's nice having variables for them. Oh, by the way, one thing I wanted to warn against, because I have a tendency to do it because typing is difficult. So I used a one-letter code. It is much better when you're programming to actually use something descriptive. So if you're actually doing this data analysis for real, give your matrix a real name rather than just R. Do something descriptive. Otherwise, if somebody looks at your code, or if you look at your code a month later, you will forget what R means. Or you'll use R to mean something else, and you'll do like a for R equal to, not realizing that R was already defined. So don't use, use nice programming stuff. Don't do what I'm doing. Okay, so now we'll go ahead and calculate our persistence. So let's go ahead and put in all of these. So we've now created our Vietoris RIPS. We'll now calculate our persistence. So this one just calculates the persistence but doesn't display it. So I can have it displayed, but what it says is it just calculated the persistence. Now if I want to see the actual intervals, we'll just go ahead and compute the intervals, and we can see that what I got was actually pretty boring. Let's go up a little bit. I go up. Okay. I don't believe there is anything we'll see in the picture, but it does, I believe, start with the highest the highest dimension first. So I'm trying to see, is there a dimension 1 listed? I don't believe there is, but we will check when we actually see the barcode picture. But you can see basically we had some things start off at time 0, 4 data points, but at time 0.08, 2 of them collapsed. We had more things collapsing, and we basically just have things collapsing together instead of, a data point appearing and then disappearing. Well, because we're talking about H0 here, we don't have any intermediate things. They're just basically collapsing into, so they're pairing up as we go on. And then eventually infinity was just our T-max. So at time 2, maybe I'd get something more interesting if, because you can see that they're pairing up by the time we get to 0.32. Maybe I should have put 0.5 as my T-max instead. Then we will go ahead and compute annotated, etc. will actually give us, telling us what is actually the generator of this. So at this dimension, vertex 5 minus vertex 2 will generate this particular one. And the one that continues on is vertex 0. Vertex 0 never gets paired up with anybody. And so we can see how the pairings are occurring. That 2 gets paired with 5, 5 gets paired with 6, 2 gets paired with 0. And so we're getting this sort of pairing right here. Okay. And then my Betty numbers were giving me a problem, and I must have not cut and paste correctly something, so we will skip the Betty numbers for now. We'll do that when we do our witness complexes to see the Betty codes. I realized I didn't have those in, so I threw those in very last minute and didn't check them out. The rest of the stuff, though, is checked out, so this should work. This is where we'll actually get to see our barcodes. I think we do still get to see, let's see, these are just setting the barcode, the options. So that's, when I copied and pasted over, this is the problem, is when you copy and paste from, in most cases I was able to preserve the formatting, but I guess there had been a formatting change that I didn't catch when I put this into PowerPoint. So now it should be fine. And if I now put in all my other options, so we did options, file name, we get, and options, did that also get, yes, the minus sign got -1 there. Yeah. So now we have all our options. We can see what is going to be displayed right here. And now if I then plot my barcodes, we can see that the barcodes are plotting. And because I'm working remotely, I have to get my barcodes. So let's go ahead and do an ls minus LRT. I have the small underscore data. So now I'm going to get my small underscore data dot png. And when I go to my data file, that should now be there. Created today at 12:17. And so now we can see what our barcodes look like. So with my 7 data points, we somehow didn't manage to create a cycle. So that's what our data points look like. Since we are plotting all of these, that we see that this is what our persistent homology look like, our barcodes. And the different dimensions are plotted on different plots. We have just enough time, I think, to go to that next thing and see if we're probably going to get some errors again because of those things. I don't need to load. I'm clearing my matrices C, D, and R, so I can now read in my entire matrix. So let's go ahead and go back over here and read the entire one in. And we will see if it seems to be, it does actually take a while. This is a pretty large matrix. So it didn't take that long last time I ran it, but now it's gone ahead and done it, and we can see our barcodes should actually be a little bit more interesting, and it looks like we didn't have any PowerPoint conversions. It looks like everything did work. So I can now go back in, and you will see that I have, if I do an ls minus LRT, you'll see that my small underscore data dot ping got updated. So now I'm going to get the same thing again. I was going to rename it data, but it seems I didn't. And we can now look at it again. Oh, so this one might be a little hard to see because I have lots and lots of points. So that's a bit of an issue when you have that many points, is seeing these things. If I take a look at size of R, you can see while I only have 35 data points, this is the dimension, but it's the 35 data points that I am seeing here. But we have run out of time, so that'll be it for today. We'll see if we can get better pictures next time. Yeah, the maximum filtration time is also still set to 2. So yeah, I didn't change any of those times. I didn't reset the filtration time or the dimension. They were exactly the same for my 7-point data set as well as for my 35-point data set. And that is something that one should actually play around with. And if one plays around with it, one will probably, so that's why this thing got so, I should have done a longer filtration time now with my 7 points. So, any other questions or comments? So I will see you on Friday where we will discuss turning a barcode into algebra formalism instead. That'll be a lot shorter than drawing all these pictures. So we'll have a shorthand algebra way of encoding the barcode, and then we'll start on witness complexes.